Awesome. Thank you, everyone. So my name is Hannah Arnold. I'm going to be introducing us today to the webinar. And then everything is going to be presented by Chris Garcia. And then we'll have a question at the end. So EngineSoft USA is a key partner in design process innovation. Again, our introduction today is going to be handled by Chris Garcia. Introduction today is going to be handled by me. Particle method CFD for engine cooling and other thermal applications will be presented by Chris Garcia. He's in the picture, that handsome man down there in the bottom. And then we'll have Q&A at the end. So we've been involved in over 4,000 consulting projects. Our software has been used in 1,500 different companies. We typically do over 130 different training annual conferences. Most of those have moved over virtually due to COVID-19. We're hoping to get back to in-person live conferences at some point. And we've worked with over 60 different academia and government research projects, collaborating with different people. So moving on. We were founded in 1983 by a group of engineers passionate and powerful advanced CAE technologies. Today, we're formed of over 350 experts in new technology and leaders in virtual prototyping and optimization. EngineSoft provides customized solutions and leading innovative technology to supporting clients in complex situations. So we have 7 locations around the globe. 6 of them are located over in the UK and Germany, Italy, Turkey, Germany, Sweden. There's also the UK office, and then Paris. We also have our US office here in Dallas. And we have about 10 people here working with the companies on the United States side. So here's some of our customers by vertical. You can probably see some of the people that you've either worked for, with, or around in the past. Automotive, aerospace and defense, energy and construction, industrial, appliances, retail and consumer, as well as metallurgy. So we're experts across dozens of industries. We have multidisciplinary competencies and added value services, best-in-class technologies and technological transfer, training, advanced on-the-job and support, research partner for academia and government, technological transfer projects in CE and virtual experimentation sectors. So some of our skills are fluid dynamics, fatigue and durability, crash and fast dynamics, process simulation, mechanics, high performance computing, tolerance analysis, environmental and vibroacoustics, multi-body, and optimization. So at this point, if anybody has any questions, they're free to ask about any of this that I just went over, any of the slides. Other than that, I'm going to turn things over to Chris Garcia and let him get started.
So I think a little bit of a change in the schedule. I'm James Christ. I'm a senior application engineer for EngineSoft. I do a lot of our trainings and a lot of our level 2 support for Particleworks and a few of our other products. I'm going to be doing the kind of overall slide deck, and then Chris Garcia is going to take over. He's one of our application engineers. He's going to do a live demo and show you what the software looks like and what the workflow is like for these types of problems. So let me go ahead and share my screen. And before I forget, because I always do, if you have questions while I'm going through this deck or during the live session, you should have a Q&A button at the bottom if you're watching on Zoom. You can just type a question in there. We will see that. If you're watching on YouTube, which I think a few of you are, you have to log in first to any Google account or Gmail or any YouTube account, and then you'll be able to participate in the live chat. And I think Evan's going to be watching that and relay those questions to us. Okay, so Hannah has already done the kind of who EngineSoft is, and then I'm going to be going over during this deck what Particleworks is. I know we have a couple of companies on for the first time viewing one of our webinars. A lot of the slides are going to be familiar to those of you that are joining for a second or third time. And then I'm going to go through the thermal modeling approaches that we take for these types of e-motor cooling and then piston cooling type applications. And a few of them are new with the most recent version, so even current customers might learn something today. And I'll go over a couple of case studies very briefly at the end, and then I'm going to turn it over to Chris for a live demo. Okay, and before I go into the actual deck, I did want to mention that we have an international CAE conference coming up. So this is usually a conference that our Italian counterparts do every year in Italy. So it's a great opportunity to expense a trip to Italy. Unfortunately for all of us, that's going to be held virtually this year, but it's still going to be a really great conference, and we have some great partners that are going to be presenting, including Ricardo and Ducati for some of the Particleworks content. And it's free to attend this year. It's going to be at the end of this month, beginning of next month.
I was going to go over there and try and buddy up to a few people and get a ride on a motorcycle and stuff.
Yeah, I was very much looking forward to it. I didn't have a chance to go last year, but knock on wood, hopefully next year. Okay, so let's kind of jump into what Particleworks is and what makes it a little bit unique in the CFD space. So the big thing that makes us different is we use a fundamentally different method than other conventional CFD tools that you're probably familiar with. So we call that the MPS method for moving particle semi-implicit, or now there's a fully explicit version. So we have a moving particle simulation. This is a method that has been basically specifically defined or specifically crafted to deal with oil lubrication type problems. So it's really good for free surface flows, sparsely populated domains, moving boundary problems, and we'll talk about several of those in a few slides. This moving particle semi-implicit method first edition, this is a great book if you're interested in some of the nitty-gritty of how the method works. That was written by the original guy that came up with the method. I have a copy in my library, and it's a great read. So the little bit of history, the method came out of the University of Tokyo in the mid-90s, and then the person who worked on the original method went on to found Prometech, the company that manufactures and updates Particleworks to this day. So we're the only people on the market that are using this method. Now to dive into some of the details on why it's different. On the conventional CFD side, we typically use an Eulerian approach, right? So we have a fixed grid. We might change that grid from every couple of time steps if we have a moving grid type problem, but the important thing to remember is the connections between any calculation nodes are going to be essentially fixed, right? We have these lines representing how these nodes are connected, and those are going to be relatively rigid. And then we attach calculation nodes to points in space and evaluate whatever properties we're interested in over time at a location in space. The particle methods that we're going to be talking about today, so MPS and SPH, which I'll touch on in a second, both use really the same discretization scheme. So they are Lagrangian methods. They directly discretize fluid. So it's kind of like you discretize the actual volume, and then you track that volume or clump of fluid as it's moving through space. And then the calculation nodes define where your fluid is. So they're very natural ways to deal with free surface problems and sparsely populated domains in particular. Now, once I go through that slide, the next question people inevitably ask is, well, this just sounds like SPH. I know what that is. Why is this different? And I think the best way to go over that difference is to go through the history, because that really explains where those methods came from and why they need to be different. If we look at SPH, this method was originally developed and it's smooth particle hydrodynamics for those that might not know what that stands for. It was originally developed in the 70s for the astrophysics community. So they're interested in problems where, you've got solar system formation. You might have at the beginning of the system, a continuous distribution of gas, and it's going to eventually collapse down into stars and planets, right? And these problems can be modeled as highly compressible fluids. So what they've done for SPH is they have these particles or calculation nodes that define a distribution of mass. And this is kind of what this image is showing. So it's almost like a stochastic method, right? You have this particle and it represents almost like a cloud of fluid or dust in the astrophysics case, but it can be used for any really highly compressible fluid. And what they do is they solve this system over time. They evaluate where these particles are, and then to evaluate the end result, what you do is you take the superposition of all of these distribution functions, and that gives you a distribution of density across the domain. So you can look at that distribution of density and say, okay, this is super dense. I have a star here. This is not very dense. It's an asteroid belt, as an example. And the important thing to note about this is it's a continuously differentiable function for this kernel function, which represents how strongly two particles interact. And what this means is we can have two particles literally occupying the same point in space. And what that does to the end result is it increases the density function at that point in space. The issue that people have run into with SPH methods is that they can become unstable as you're trying to do either weakly compressible or completely incompressible fluids, which is, what an oil is, right? So what Promotech did is they use a fundamentally different kernel function to describe how strongly two particles interact. So like I said, this was developed in the mid-90s by Kashizuka and Oka. And what they were trying to do is make a method that represents incompressible fluids. So what they have is a discontinuous function or an asymptotic function. So as you get very close to having two particles touching, the repulsive forces increase exponentially. And that really naturally describes an incompressible fluid. So you have one droplet of fluid next to another, they're not going to end up occupying the same point in space. The really natural way to think about this as a collection of marbles, maybe rubber marbles, because there's some elasticity there, but you can evaluate how those marbles are interacting and then see what your free surface looks like as an example, or where you have large clumps of fluid and you're going to get a lot of heat transfer as an example. Now, what does this look like for a more realistic example? Well, realistic as DMBreakers, right? So I'm sure you've seen this this example. We start with a volume of fluid here, and then we progress it through space. It's the quintessential first tutorial everyone does. And the difficult thing about doing this type of problem with a conventional tool is that you still need to discretize everywhere that might have fluid. So we end up with a bunch of elements here, and at every time step, they're just going to say, hey, the volume fraction is 0. So it's kind of a waste of computational resources in a sense. And another thing is, before we start the simulation, we might not know how much splashing we're going to get and whether fluid is going to escape this container. With a finite volume code, you need to decide that in advance and discretize up. With MPS, you can just draw a larger domain, but you're only paying a computational cost for the amount of fluid you have and the size of the particle you're using. So you can draw an arbitrarily large domain and not really pay a computational penalty for doing so. You can also a lot of times use a finer resolution and have that resolution continuously throughout the domain. So some of these small features we might not have discretized small enough on this side, but we're able to resolve those features using MPS. Now, when we put all of this together, the really nice thing that comes out of it naturally is that we're able to deal with moving boundary problems very naturally. So because we don't have to deal with a changing grid over time, we can just say, here's a particle, here's a wall, if that wall moves, it's just going to apply an appropriate repulsive force to the fluid, and it's going to move appropriately. So there's really no additional effort required, either computationally or from the users. On a user side, you basically just tell the system, hey, this is moving, maybe it's rotating this fast, and that's about it. And one thing I always mention, because I get this question quite a bit, is what does the post-processing look like? And that's completely integrated within Particleworks. So it's not like some other tools where you need to have a solver in one spot and then use a separate tool for post-processing. And sometimes that can create workflow issues. There's built-in post-processing. And I think in the video that was playing before we started, while we were waiting for people to trickle in, it was mentioned that Prometech does like advanced rendering, and that's actually a module that's available now. So you can basically export simulation results to an animation program like Blender, which is free, or 3ds Max or Maya. I think those are the two professional ones. So maybe your marketing team wants to use these to sell engines. Now, where is Particleworks used? I guess the biggest sector, I would say, is automotive, and that's kind of what everyone is here for today. You might have friends in some of these other industries, and we do see use in quite a few other industries. Anywhere where you have an incompressible fluid, anywhere where you have complex moving boundaries, these are all areas where Particleworks can make a lot of sense as a simulation tool. Okay, so now we've got kind of the foundation out of the way. We can move forward. We can march ahead and talk about the thermal modeling approaches that Particleworks has. So I do actually see a question in here in the chat, so I can answer that now. So looks like Anthony asked, what are the geometry requirements for rotating moving meshes? And that's one of the nice things is we just bring in an STL. And then Particleworks has a pre-processing step that's completely automated. You basically just tell it, run the system, run the pre-processing, and it converts that STL into what we call a distance function. It's similar to that kernel function I was talking about earlier, where you basically have a curve describing how strongly a particle is going to interact with another particle. Very similar thing for walls. So Particleworks converts that STL geometry into a distance function, and beyond that, there's no other geometry requirements. Okay, so different thermal approaches, right? We can do direct thermal simulation. We can do heat transfer coefficient simulation and then export that to a dedicated FEA tool. And then we can do internal conjugate heat transfer. So I'm going to talk about each of those in turn. Going first with direct thermal simulation. Let me restart these videos. So this is an e-motor cooling example that we have. This is actually, I believe, from one of the case studies I'm going to be talking about in a moment. Well, let me start these up again. So one of the things that we can solve as a parameter for each particle, or as a solution output for each particle, is the temperature. So what we can do is turn the thermal solver on, specify some thermal boundary conditions like the initial temperature of the fluid, the initial temperature of geometry as an example, and then we'll get heat transfer from the walls of the geometry onto the particle, or cooling as the case may be. And what we're seeing on the right here is an example where instead of using that distance function I described, we're using actual particles to represent the geometry. This use case isn't as common anymore, I would say, especially with the new conjugate heat transfer solver, but this does a really good job of showing how the particles can change temperature over time. So what we do is we spray a cool fluid onto a hot set of particles, basically, and then heat is transferred from these hot solid particles into the fluid, and we see that temperature gradient happening. And we can also do temperature dependent fluid properties. So it's we consider it to be part of our non-Newtonian set of options. So you can do either a script, a JavaScript function to describe how temperature depends on, or how like viscosity is going to depend on temperature, or you can use a simple table from Excel. And then we include shear heating that's going to be relevant for some problems. So, and now the video, please. Okay. So the other option that we have is, this is probably today the most commonly used approach. So one of the issues that people run into when they're trying to do the direct thermal simulation is that the time scale that you care about for fluid quasi-steady state versus thermal steady state is going to be different, right? You might have a gearbox that has a pretty consistent flow pattern on the order of 5 seconds, but the temperature isn't going to stabilize for half an hour, just as a wild example. So in that case, you don't want to run the whole fluid simulation for half an hour, and running in 5 seconds might give you enough directional data on how temperatures are moving, but it might not. So you have to kind of make the engineering judgment call as to whether those timescales are appropriate. And in the cases where those timescales just don't match up and it's not going to be feasible to do the direct thermal simulation, or it's not going to be time efficient, what we do is, instead of directly solving for temperature, we'll solve for heat transfer coefficients and then map those heat transfer coefficients onto the walls. And that's what this case study that we have was doing. So in the piston gallery, they solve for heat transfer coefficients, map them onto the gallery walls, and then they can take that mapping and use it as an input into an FEA thermal model. So a lot of our customers are doing, Particleworks and then ANSYS Mechanical. Any thermal solver is going to be able to take our input data, it's just a CSV file, and then they'll be able to do oftentimes a much longer time scale simulation very quickly. So those are often steady state simulations, they run pretty quick, and you can split up the system and let each solver do what it's best at. This is a really good graphic of what these types of simulations look like. So what we've done here is fixed the camera position to the piston. So we're kind of keeping it centered, front and center in the camera. And then on the left, we're looking at the heat transfer coefficient on the particle itself. And then the right image is going to be after we map that onto the surface, the inner surface of that gallery, right? I'm not sure how well this is playing. It's getting a little choppy on my end. Let's move forward. And we do, so that workflow is possible with any solver, any thermal solver, because we just give you the raw output that you need. So the position of a given measurement and then the value. You can map those into any FEA mesh that you have. For our ANSYS customers, which I know a lot of you are, we have a direct plugin that makes that workflow a little bit easier. So you can basically set up Particleworks inside of Workbench. There's a module for it, then you set up your Particleworks problem, and you can just use like you draw the arrow from the Particleworks block over to the ANSYS Mechanical block, and it'll bring everything over, and it saves you a couple of steps. So if you're doing it every day, or this is all of your simulations, then it's often a good workflow time saver. And the same thing can be done, actually, I'll mention it because it's on the slide. You can do pressures as well, in addition to mapping the heat transfer coefficient. Now, when we're doing all of these heat transfer calculations, the default that Particleworks has, and this was the only way to do it up until the most recent version, was to use a default Nusselt number correlation, which was based on flow over a flat plate. So parallel flow parallel to a flat plate. That was the for both laminar and turbulent flow, there's different correlations, but those are the assumptions that were being baked in. Now, let's say you have either from institutional knowledge or maybe your problem is just inherently not valid for that correlation. What you can do is define your own. So Particleworks really tries to make it so that you're paying for the solver, and then any input data, you're able to control. It's not, they try to not make it a black box, which I really appreciate. So all of our functions are going to be just JavaScript things. There's no proprietary languages. And one good example of when this is applicable is maybe for impinging jet flow. This is going to have different heat transfer behavior. And this compares using the default laminar flow correlation versus using an impinging jet correlation. So a lot of these, you might have textbooks or, like I said, institutional knowledge for what correlations work for your problems, and you have the freedom to do that. Now, this is a very exciting functionality. It was, again, added in the most recent version. So we're really excited about what our current customers are going to come up with on using this feature. And I think during the CAE conference, we're going to have at least one presentation talking about use of this in the wild, right? So what we do for conjugate heat transfer, I guess let me step back. So normally when we're using these distance functions, they're pretty simple boundary conditions. You can set like a temperature on them, but you're not really resolving any interior space for them. But what we can do is, when we're using a conjugate heat transfer solver, is we discretize the entire domain into a fixed grid. So this is a two-dimensional slice of what this looks like. We can set the size of these cells independently from particle size, but then it's going to fill the domain with these voxels, they're called. And then for each voxel, the solver is going to evaluate what the volume fraction of material versus empty air, essentially, what that is, what the surface area of it is, and then from that information, it's able to pass heat from particles to these voxels or these cells, and vice versa. So by doing that, we can incorporate conduction between adjacent cells and resolve heat transfer interior to geometry. So there's kind of trade-offs and advantages to using this approach versus using a dedicated FE solver. So on the one hand, you're giving up a little bit of control over what this grid looks like, but on the other hand, it's the workflow is a lot easier because you don't have to worry about dealing with moving boundaries or dealing with really complex geometries. That's kind of handled for you by this fixed Cartesian grid approach. And that evaluation of whether a given cell contains geometry, and if so, how much, that's going to happen at each time step. So there's no additional work required to deal with a moving boundary. And that's actually the example that Chris is going to be doing at the end, is going over a moving boundary problem. Now that's all kind of theoretical, right? But here's what it looks like in a more realistic use case. So I don't know if everybody else is, but I have my cup of coffee, and it's staying warm in the mug that I have. But depending on the material of the mug that I have, it might heat up the mug too much. So we can evaluate this with Particleworks. We have this discretized mug here, and we're seeing the temperature gradient happening over time as thermal energy is passed from the particles into the mug. Let me do a quick check for any other questions. Evan, before I move on to some of the quick examples, do we have anything from the YouTube chat?
At the moment, no, we do not.
Okay. So let me move forward. Okay. And if anybody is interested in the full papers, these were all presented at conferences. You can contact us after the webinar, and we can get you a hold of these papers. So the first one I wanted to touch on is drive system design. So they were working on an e-motor with some of our Italian counterparts, and they wanted to evaluate thermal performance because, as the e-motor guys on the call are very familiar with, the performance and efficiency is tightly coupled to the operating temperature, right? So what they wanted to do is incorporate these moving boundaries, right? You have the moving rotor and some complex geometry that can be difficult to mesh. So they set this up with the help from our counterparts, and were able to evaluate the thermal performance. And they used the approach that we had talked about earlier by solving for heat transfer coefficients in Particleworks, and then moving those over to an FE solver. And they found excellent results. They did a comparison between Particleworks and a mesh-based CFD tool, and you can see in this chart here the difference in computation time. So because we're using a little bit more efficient description of sparsely populated domains, we end up with often less calculation nodes, and oftentimes we can take larger time steps than some of these mesh-based codes. So we're faster in that sense. And then we're also GPU optimized. So in the final row, you can see the significant increase in speed by using by today's standards, these are relatively modest GPUs. So by the end of writing the paper, they were already confident that it was going to really increase the ability of them to optimize their motors. And there's going to be a similar presentation given at the CAE conference from Ricardo. They're going to be doing an example of what they're using Particleworks for on their e-motors. And then on the piston cooling side, so I think we've already seen this representative example. I think this is from an example model. I don't think it's from the actual piston that they used for confidentiality reasons, but this is the kind of system that Wärtsilä used. So I believe this was Wärtsilä is Sweden, I think. So they were looking at the internal temperature, the heat transfer coefficients inside the inner parts of this piston. So you can see the blue portions are what they mapped heat transfer coefficients onto, and then in their FE solver they solve for the temperatures at a handful of nodes and compared to a physical test model that they built and then ran in their lab, and they found excellent performance. So they don't have the actual numbers on here, again, for confidentiality reasons, but they ran through a whole suite of tests, and this is from one of them. They found the trends were, on point for comparing between the Particleworks model and the lab model. And again, by the end of writing their paper, they were already talking about how they were using Particleworks to do work on their actual pistons, and they identified actually some problems that they were going to have with one in-design piston, and they were able to take corrective action, check that was going to work in Particleworks, and then fix geometry before it goes into production. And again, they did a comparison between MPS or Particleworks and a VOF method, so that's volume of fluid. And again, they found a very similar trend to comparisons with finite volume, that the time difference in calculation is just pretty massive. And the computational requirements tend to be a lot lower. So you can see 160 cores versus 12 cores and 5 versus 24 hours. Oh, and the other thing I wanted to mention, so Ducati is going to be presenting something very similar, their application for Particleworks in piston cooling at the CAE conference. So with that, I'm going to pass it over to Chris Garcia, and he's going to show you around the software interactively a little bit.
Hey, real quick, I got a question for you. Is there a limitation on model geometry size?
There is not.
Okay. Just wanted to clarify that for everyone. Thank you.
Absolutely.
All right,
And while
perfect.
Chris is pulling that up, oh, I was going to say, Chris, if you want to pull in the geometry, Particleworks brings in STL and OBJ geometries, so you can export those from any CAD program. And we always recommend that people don't do geometry simplification. It's not necessary with the preprocessor that we use, and it's going to increase your workflow or the speed of your workflow a lot by not having to do that tedious step.
Yeah, that's actually a good segue, James. Let me just make a quick adjustment so I can make my work a little bit easier. But like James had mentioned, there's no special step that we need to take in bringing in geometry. So let me go ahead and just bring in some quick geometry. This is going to be our piston geometry, and this, like James had mentioned, this is going to be a moving boundary problem. So just like that, we've already got our geometry in. I don't have to do anything special. The only thing I have to do is make things a little clear so that we can see what the heck is going on. I know that's always been one of the biggest things that I've come across in industry is, well, how can I see what's going on? Well, here we go. Now we can see it. This is a pretty cool trick. One thing I really enjoy about Particleworks is that bringing all this stuff in is very easy, and manipulating how we see things is very, very easy. So from that, I do appreciate the hard work that all the guys in Japan had done. Makes my life a little bit easier. So let me just kind of change some physical settings here for a second.
So while Chris is kind of setting up the moving portion of the moving boundary problem, I'll talk a little bit about how we do those. So we use this concept called keyframes, and what that basically is at a given point in time, we're going to specify this is how fast this thing is moving in some direction, or this is the position that it has, maybe the rotational speed that it has, and we can stack relative motions. So you'll end up seeing Chris create some basically dummy groups, and that helps us basically connecting two parts. So you can have motion on one component and then motion on another component that's relative to the first one. So that becomes pretty necessary when you're doing these somewhat complicated motions for a connecting rod and the corresponding piston. It's relatively straightforward to set up. You basically just have to specify this is going to be moving up and down, this is going to be moving side to side, and like anything, there's always a couple of different ways to do it.
Yeah, that's a good point. And I'll get there here in a second. Before I get to the animation and stuff, one thing I'd like to point out is kind of referring back to James's original introduction slides about having to figure out where the domain or where the particles are going to exist in this domain. I have no idea where these particles are going to be shooting in this domain. In fact, they're going to be coming out of this little inflow here, but I have no idea where these things are going to be coming from. So the only thing that I'm going to do is make sure that these particles exist inside of this domain. So I'm actually going to increase this domain size a little bit. And just one more time for emphasis, I have no idea where these particles are going to be shooting out of. I have no idea where they're going to be traveling. So I'm just going to make my domain large enough to where my particles exist within this system here. So at no point have I spent any time messing with any mesh, any figuring out where stuff is gonna have to be. And I know from previous working experience, sometimes that stuff can get pretty tedious. So there's a great advantage. One of the things, again, I really love about Particleworks. I'm going to go ahead and kind of create some oil and wall properties. And this stuff is really easy to define. Go ahead, James.
So the domain, it can be sized pretty much arbitrarily. One thing that it does is it really just acts as a pseudo outlet. So any particle that travels outside of the domain is going to be, removed or deleted from the system. That can be really convenient just to avoid having to create your outflows. If you have one spot where everything's going to leave, you can just chop the domain there, and then particles will automatically be removed.
Yeah, I know that comes in handy, especially when we have some large models and we don't really know where everything is. So we can set a domain as needed and then go from there. So while James was kind of explaining that, I've already set up some physical properties for our oil, for our adiabatic walls, and our piston, which is actually where we're going to do the conjugate heat transfer and the HTC calculations. I've already set those up in our property managers, and I've assigned for the piston, I've assigned our thermal boundary and our adiabatic walls here to our cylinder and our connecting rod, and I've given our inflow the oil physical properties in this model. So just like that, we're halfway through the simulation, and we've been here maybe 5-10 minutes if that. So kind of shows you some of how fast this stuff can go. Obviously, there's a little bit of hands-on that you'd have to do, but it's really easy to grab, and yeah, I really enjoy that. So I'm just going to kind of do a little bit of physics here. I'm going to define a volumetric flow rate, and then go from there. I'm going to actually change this temperature as well. That way we can actually have some heat transfer going on here.
Yeah, a solid half of the time I do these, I forget to set the initial temperature, and then I start previewing results. I'm like, why is everything 0?
Yeah, I've run into that myself.
You get rapid feedback, so
you'll figure out what's going on real quick. So so now that everything is set up, now we'll kind of go through some of the animation stuff. Like James had mentioned, you can create a couple of groups, or dummy groups, as I like to call them. And this will basically just kind of group some of the pieces together, and you can do some of your keyframes fairly easy, and you won't have to individually define these as you're working. In this particular model that I'm working on, I've got some sample scripting. These are, again, JavaScript, non-proprietary pieces of information, so these can be shared and whatnot. In fact, let me kind of show you what's happening as I'm entering these in. So that way we can kind of see what's happening here. And that's still a little too fast. Here, just like that, we've already got a little bit of translation described here. And as we keep going through this example, you'll kind of see all the stuff come together. We're good there. Again, I've got some of this stuff handy already, so if you're really good at this stuff, you can type this stuff out as you're going. For this case, I don't want to mess up the presentation, so I've got this stuff handy and ready to go. Change this over to rotation. Right. And now I'm going to make this a child group. And we're going to do the same thing with our piston.
So this is essentially just stacking reference frames relative to each other, and that makes it really easy to set up complex motion.
Here we go. Just kind of give an example. There's some pretty complex motion right there in this piston example, yeah, that's the majority of the problem right there. That's I know that can be pretty difficult to do, especially with moving grids. With Particleworks, we don't have to worry about that. We're good to go. We're gonna make our bosses happy, and I think everybody likes to do that right there. So we'll be able to get some good results, get them quick, and keep going. So here I'm just going to define some of our modules, some of our physics modules for Particleworks. One of these modules are going to be, or a couple of these modules are going to be some of the thermal modules that James was speaking about earlier. And for instance, this is going to be the thermal module, and we're going to go ahead and turn on our conjugate heat transfer module. And I also want to turn on our HTC, our heat transfer coefficient. If for whatever reason we wanted to do like a script, kind of like James was saying, on getting some more finer correlations on our heat transfer coefficient, we can do that through the scripting. But for this example, we're just going to keep it simple and just leave it as HTC here. And I'm going to go ahead and change some of our simulation times. Get everything set up. Everything is good. I'm going to pre-process and go ahead and start our simulation. Pre-process is kind of what James was mentioning earlier about creating the distance functions between the wall and the particles, and I can actually kind of show you guys what James was talking about earlier. Let's just go ahead and take a look at our piston here. In these blue and white regions, this is what we're going to call our distance function. This is going to be that interaction between the particles and the walls. So we'll see that this runs fairly quickly. It's working smoothly. And while that's working, I'm going to go ahead and pull up a completed model already. That way we can have some interesting stuff to look at while this thing is running. I actually ran this one a little bit longer. Let me change the camera position. That way we can kind of see what's happening. Let's move this to our piston. In this particular case that I did, I actually used some post-processing tools to kind of get HTC mapping on this piston. Let me turn that off for a second. Here, move this where you can see the piston gallery. We'll change this. There we go. Now we can kind of see some of that distribution in there. While this is running, I guess, James, we can open back up to any questions.
Yeah, and I think I have one question. Now, did you run this on a supercomputer, or what kind of hardware did you need to run this?
So I've got just a decent sized laptop. I've got it's a 16 core, 8 GPU, nothing too fancy. It's definitely nowhere near a supercomputer, that's for sure. You know, nothing too fancy on my end, and I was able to solve this in a pretty short time.
Good. So I do see one question about flow through small passages, and that's something that's absolutely doable. It really just comes down to selecting an appropriate particle size so that you're able to resolve that flow. So our typical recommendation is anywhere between 3 particles and maybe 10 or 20 particles across a passage to fully resolve that flow. And if I'm not sure who asked that question. That might have come from YouTube, but we can have a more in-depth discussion offline about your individual problem and approaches for modeling it. And Chris, if you want to switch back over to the one that we had just set up, and folks can see how far or how quickly you're able to get results and
this is likely
immediately get feedback.
This has likely been covered, but this question came in through a different chat earlier. I didn't see it right away. How should I approach setting up a thermal analysis problem in Particleworks? I'm sure that's probably what y'all were just showing, but just wanted to make sure that we got that out there.
Yeah, so there's kind of the three different approaches, and it's going to depend on your individual use case as to which approach is the best, from doing a direct thermal simulation and evaluating the temperature of the fluid versus doing heat transfer coefficients and then an FE simulation, or doing direct conjugate heat transfer. So the setup is relatively similar for all of them. You just have to basically check the checkbox for include this solver output. But then actually choosing which approach is the best is something that we do on a more of a case-by-case basis.
Thank you, James.
And I think the nice thing about what Chris is showing here is that we can do kind of quasi post-processing or actually even full post-processing while the simulation is still running. So it's not like we have to wait for the whole thing to finish before we were able to get results. And then, half of the battle is making sure that, you set your material properties right, as an example. So by being able to get that rapid feedback, you're able to sanity check the numbers you're getting and make sure that you're not running a simulation that was set up incorrectly.
Yeah, I think that's a good point to make there, James. And I went ahead and started up with some mapping, post-processing. Nice thing about Particleworks, it queues it up, and so once this simulation is done, it'll go ahead and kick in that post-processing, which this simulation should be wrapping up fairly soon. So we might see that before everybody has to go. But in case we don't, let me turn this off for a second. We'll see some mapping results that I've done previously. This is post-processing for temperature values. See a little bit here.
So this is a step where we're essentially taking the geometry and mapping or taking the average of its neighboring particles at a given point, and then graphically applying that to the surface of the geometry. And in a lot of cases for certain geometries, that can be a lot more useful of a way to ingest information rather than just looking at the particle values and the colors of those particles. So I think that wraps up most of the content that we wanted to show. Again, we'll stick around for any questions, and I think everyone's going to get an email after this, probably with the recording, and then also with our contact information. I know whenever I think of a question for a webinar, it's as soon as I click the exit button. So feel free to email us, and then there's a lot of additional information on our website. I think with the email we send out, we can include the link to register for the CAE conference. There's going to be some really great presentations by customers showing off what they're working on with Particleworks and with a variety of other tools. So I'm not seeing any other questions in the chat. Hannah or Evan, do you have any others?
No, I have actually managed to burn through everything that has been sent to me. So luckily, we managed to be able to answer all of that stuff for those people and give them the opportunity to get the information they wanted.
Yep, and no more
Excellent.
questions from YouTube.
Perfect. I'm going to go ahead and stop sharing, and we'll leave it for closing comments.
Good. So I think that covers everything. We'll send out those emails, and please let us know if you have any questions.